You are in mute, sir.
All right. So since I disabled everyone from talking or unmuting, it disabled me also. Okay, I'll be sharing my screen now, and we shall proceed further. And before we proceed further, we need to talk about a few things. Let me share my screen. So I believe now you are able to see my screen and you all are able to hear me. I request you all to, for one time, please comment on the chat window on whether you all are able to hear me or not. Wonderful. So friends, the session is getting recorded and it will be placed on your learning management system for your further consumption. And we are going to add a lot of new things. We have actually done that. We have added a lot of new things into this training so that you guys understand new aspects of deep learning and how AI applications are eventually built on top of that. Before we get started, I wish to quickly introduce myself so that you all have a sense on who I am and what is the background that I'm coming from. Let me stop the screen share if I can. I think I need to do
because a lot of people were saying that you speak, you enable your webcam, but then you appear very small. Okay, in a small window. That's because I speak from mobile. I don't talk from laptop because that would be at a certain distance from me. And I believe the sound communication would not be clear. I usually use a Bluetooth to speak during meetings. So for those of you who are not aware of who I am, this is me. I'll quickly introduce myself on LinkedIn and then we shall take it.
Okay. So let me share my screen now. Okay, this is my LinkedIn profile, friends. You can just check that. I'm an Industrial Revolution 4.0 implementer, a chief data scientist, and technology advisor on 4 different companies. I have master's degree both from IIT and Indian School of Business, and I have 16 plus years of experience. I worked with HSBC, ITC, Infotech, Infosys, and Deloitte. These were the companies that I've worked with in the past. Of course, that we formed these companies, InnoDataTechs, for delivering projects, and 360DigiTMG to deliver the trainings. That's pretty much about me. If you want to connect with me, here we go. You'll find a lot of high, I would say, head of departments of different companies, etc., on my profile, just in case you want to serve on that particular network that I have. And here, if you see, I have 27,490. 30,000 is the limit of LinkedIn. Nevertheless, if you want to connect with me, please do so. After a while, after I reach 30,000, you'll not be able to connect with me. You'll only be able to follow me. Okay. And yeah, these are a lot of amazing students who are getting placed in various companies. Sandeep got placed as data engineer, etc. And if you go to our page, you'll find a lot of success stories. These are the various people who got placed just in a matter of 1 month. Okay, in various companies, and a lot of other people who got placed. They were like, please do not share my details on social media. Okay, otherwise I would say good 20 odd people get placed every month, but more than 50% of them are working professionals. So they are a little taken aback when we say that we want to share your photo, your LinkedIn profile on social media, because they feel that we did not really tell to our senior management that we got trained on data science and then we got placed, right? So for some reasons, they are not keen in having their details posted on our website, our social media. Apart from that, at least good 40% of students who got placed, their details would be there. On our website also, you have, success stories. I were to scroll down a bit. This is called as lazy loading, so it will take a while, but it will come up. Come up, please. Yeah, it has. So here you have these success stories. When you click on that, you'll have a booklet in which you'll have list of all the people who got placed until now and their LinkedIn profiles. You might want to click on that. You might want to connect with them and then check with them if there are any openings in your company, etc. Anyways, our HR department is in touch with all of these folks. We maintain a very good camaraderie, a very good relationship with the people who got trained with us in the past. So will we do with you all as well. Okay, so let's get started with this. Agenda for today's session is that we are going to get started with artificial intelligence, which is usually built using deep learning algorithms. Okay, you have traditional machine learning algorithms and you have deep learning algorithms. Today and tomorrow, our emphasis will be on deep learning algorithms. We will understand when we say deep learning, it is nothing but neural networks. And when we talk about neural networks, we'll speak about the neural network primer or deep learning primer, wherein we are going to understand the basics, elementary stuff. And slowly and steadily, we are going to build on top of the concepts. And we'll get to a stage where we understand all the finer nuances, all the finer detail information about all the various terms and terminologies and lingo that is used in the field of deep learning. Once that is done, our focus will shift onto the algorithms. We are going to talk about artificial neural network. We'll talk about convolution neural network, and we should talk about recurrent neural network. Okay, we want to give more meat, more information to our students who joined or who enrolled for data science program. And once that is done, students who want to upskill for professional course can always do so. And students have already enrolled for professional data science and AI program would automatically switch over to the AI program. Okay. But this is something which is very important in a lot of job openings. People are talking about deep learning. People are talking about neural networks because this is a revolution in its own. And the kind of research which is happening in this space is tremendous. So if you want a job, it is as simple as that you need to understand every bit of what is being taught to you guys as part of the neural network program for today and tomorrow. Okay. And if you want more salary than what you would have otherwise got, then also this is very important. This knowledge is extremely important. All right. So let's move ahead. In order to accomplish deep learning algorithms, when I say deep learning, it is synonymous to neural networks. Neural networks or deep learning mean the same. If you want to accomplish deep learning algorithms, or if you want to execute deep learning or neural network algorithms, then you should be making use of some libraries. What is a library? Library is collection of books. For us, when it comes to data science and artificial intelligence, when we say library, it is collection of code, collection of programs, collection of functions, which someone else has written in the past. And they have put those in libraries. And we will be installing that library on our computer. When we install the libraries on a computer, you can make use of all the code, all the programs, all the functions which someone else has written in the past. Right? Someone else has written in the past, so you can readily make use of that. Like in libraries, you have books, someone would have written something, you learn and implement that. On similar lines, we are going to reuse the code. We have something called as TensorFlow, which is one of the deep learning libraries. It was introduced to the world by Google, and still Google is trying to enhance this library further. Of course, Python will be our de facto programming language, which we'll be using to write the code. And within Python, we will install TensorFlow and we'll write the code. We have on similar lines to TensorFlow, we have Theano, we have Microsoft Cognitive Toolkit, we have Keras. This is CNTK, just remember CNTK, which is the deep learning library from Microsoft. Then you have MXNet, you have PyTorch, we have Cafe, we have OpenCV. OpenCV is used for specifically image processing applications. It is used in implementing image processing applications, OpenCV. There are a lot of other deep learning libraries which are emerging or which have been in place since long, but not many people are using it. The libraries which are extremely famous when it comes to deep learning includes TensorFlow, Keras, and PyTorch. Nevertheless, we should not just bank on theory, right? We need to do quick research to understand, hey, is that true? Whatever this gentleman called Barani is talking about, is that really true, right? So go to Google Trends. You can search the terms. Let me search TensorFlow. And let me pick the data for the last 5 years. This is a trend, or we can also take it from 2004 until now. Let's see. Okay. What does this mean? This means that TensorFlow was introduced to the world way back in November 2015. Okay. And why are we looking at only India? Let us search worldwide on what is the demand for TensorFlow and see what was happening. So roughly in November, Google has launched TensorFlow and they made it open source for people to reuse the code which they have written. And until I should say, 2019, April or March, the demand for TensorFlow was at its prime. Then what happened was demand was slowly coming down. Why? Let's see. Keras. Keras is yet another library for deep learning, for accomplishing deep learning. And if you see this, Keras was introduced to the world even before TensorFlow was introduced. A guy called as Francois Chollet, that's the name of the person. He's the person who has come up with Keras. TensorFlow is called as low-level programming language. Low level means you need to have thorough understanding about programming, thorough understanding about coding. If you have been into this business of writing code for decades, or maybe at least a few years, then you'll find it easy to write the code in TensorFlow. But Keras is not like that. Keras is something which even business people can use. Very limited code is what you need to know, and very, very basic. And you can accomplish deep learning libraries. And hence, Keras became very popular. A lot of people started using Keras. And the beauty with Keras is that it is high-level programming language. At a very high level, if you have understanding about the programming, that is sufficient, friends. Your job is done. So what Google has done is slowly, it has acquired Keras. In some sense, it has acquired. Acquired doesn't mean paying and taking it. Both are open source. So what they've done is TensorFlow, which is Google, has approached Francois Chollet and they've made Keras. Francois Chollet is the father of Keras. He came up with this library called as Keras. So they have taken Keras and they have made it a bundle. So if you install TensorFlow, Keras also will automatically get installed. Now, from TensorFlow version 2 onwards. Before TensorFlow version 2, TensorFlow and Keras were two different things. Okay, officially, there were two different things. TensorFlow, Keras. Officially, they were different. And then Keras is what people used to prefer because when you write the code on Keras, it is very simple. However, in the backend, it makes use of TensorFlow. Okay, and it executes the code. Whatever code you write, it will go into the backend. It will convert the code into TensorFlow code and it will execute. But you need not worry about all that. Why should you even be bothered about that? We as business users believe in solving business problems. We believe in, building AI applications. We are not programmers. We are not coders. We are data scientists. We are AI experts. Okay. But the demand for Keras is also more or less in sync with TensorFlow. Why is that? Is there a new kid? Is there a new kid in the market now? Oh, yes. What is that kid called as? PyTorch. If you look at this, 2020, May 2020, PyTorch has overtaken Keras and it has also overtaken TensorFlow. Now, today as we stand, PyTorch is extremely preferred in comparison to the combo of TensorFlow and Keras. TensorFlow Keras is one combo which people use. You write the code using Keras, it executes the code, it converts that code into TensorFlow and executes. PyTorch is yet another library, deep learning library, which is far superior. You can look at different countries, in which country, to what extent people are using Keras, etc., etc. And if you see here, majorly in Malaysian market, etc., people are still using Keras extensively. Indonesia, this is what Malaysia. Yes, there somewhere Singapore will be there. They also, I think, are Keras extensive, and rest all are TensorFlow, etc. And though PyTorch has smaller market, the number of people who are using PyTorch, though PyTorch has a smaller market, a lot of people are adopting and the demand for it has increased, skyrocketed because of one key reason or two reasons. Number one, when you write the program in PyTorch, it is as simple as Keras. Writing code when it comes to Keras deep learning library is very simple, but it is slow. Keras is considered to be a little slow because it has to convert that code into TensorFlow and then execute. It will take some time. Whereas if you use exclusive TensorFlow, it is very fast. Because directly you're writing in TensorFlow, the execution will be fast, training will be faster. But you need a lot of programming knowledge because you need to write lengthy lines of code. If you can accomplish a specific task in 3 lines of code in Keras, in TensorFlow, you need to write 10 lines. 3 lines of code, job is done in Keras. In TensorFlow, you need to write 10. So that's one drawback with respect to TensorFlow, but it is fast. TensorFlow is fast. Keras is easy. TensorFlow is fast, Keras is easy. Both of these are there in PyTorch. So writing code in PyTorch is easy. It is as simple as Keras, and it is as fast as TensorFlow. So the combination of these two, I mean, the good things of TensorFlow and Keras, both of those are available in PyTorch. This is the reason why people are preferring PyTorch over TensorFlow Keras. But I should say today as we stand, it's 50-50. But when you put on your resume, would people prefer you if you say that you have knowledge about TensorFlow, Keras, and PyTorch? Or if you just say that you have knowledge about any one of these? It is called as economies of what? Economies of scale. Sorry, economies of scope. What do you mean by economies of scope? The more you know, the more I'll pay you. If 2 profiles come to me, both are equal, assume. But one person says that, you know what, I have knowledge about only PyTorch. Another person says, I have knowledge about PyTorch and TensorFlow Keras combination. Then whom will I prefer as an interviewer, as an employer? I would prefer that person who has knowledge about both. Economies of scope. The more you know, the more I pay you. Okay, so this is in short about the deep learning libraries. What are the libraries which are in demand now? How each one of those differ from one another. Okay. And you have other libraries such as Caffe, MXNet, etc. Not that widely used, but still they exist. Okay. So here we have this project management methodology, but the world has evolved from CRISP-DM to CRISP-MLQ. The first step is understanding the business problem and data understanding. These two are part of one single step in CRISP-MLQ. This is CRISP-DM. Sorry, friends, for some time, maybe for another 30 minutes or so, you need to bear with me. My scribbling pen is on its way. I forgot it at my parents' place, so it is coming, it is reaching me. So until then, you need to bear. Otherwise, I have a habit of scribbling, writing everything that I talk about. But just bear with me. I'm sure things will fall in place once I start writing. Okay, these two, business understanding and data understanding, belong to one phase in CRISP-MLQ. This is CRISP-DM. This has 6 phases. 1, business understanding. 2, data understanding. 3, data preparation. 4, modeling. 5, evaluation. And 6, deployment. In CRISP-MLQ, also we have 6. This is CRISP-DM. CRISP-MLQ is an advanced version of CRISP-DM. It's the next version of CRISP. And CRISP-MLQ also has 6 phases, in which These two, business understanding and data understanding, belong to one phase. Then phase 2 is data preparation. Phase 3 is data modeling. Phase 4 is evaluation. Phase 5 is deployment. And phase 6 is model monitoring and maintenance. So you'll have 6. Model monitoring and maintenance. Look at that later. So friends, this detailed curriculum, you need not worry too much about it. It should have been named as detailed list of algorithms. So we have multi-layered perceptrons. We will have computer vision, self-driving cars, convolution neural networks, pre-trained models, visualizing convolution filters, hidden layers, recurrent neural network, bidirectional recurrent neural network, deep bidirectional recurrent neural network. Then you have CNN, RNN models. Then LSTM, long short-term memory. GRUs, gated recurrent units. Bidirectional LSTM, bidirectional GRUs. Deep bidirectional LSTM and deep bidirectional GRUs. Autoencoders, RBMs, DBNs, restricted Boltzmann machines, deep belief networks, which are not widely used now, but yeah, they exist. VAE stands for variational autoencoders. Then you have generative adversarial networks, super resolution GANs, speech recognition systems, reinforcement learning, Q-learning, deep dream, genetic algorithms, chatbots using RASA NLU. These are the new breed of algorithms that I've listed down here. These are part of very advanced natural language processing algorithms, sequence to sequence, attention models, transformers, BERT, GPT-2, GPT-3, GPT-4, 5, people are already working on that. A company called as OpenAI is doing that. You have T5, ExcelNet, bunch of those exist, right? Auto AI, Auto ML is yet another thing, and explainable AI. So friends, from Monday onwards, every day for 1 hour, from 7 to 8 p.m. Okay, from 7 to 8 p.m. every day, we are conducting this session, which is called as Auto AI, Auto ML. Okay, and I'll also talk about explainable AI. If you're interested, you can join. We can also do one more thing. We can also conduct from 6:30 to 7:30, so that if you have any batches, any trainings from 7:30 onwards, you can also attend those. 6:30 to 7:30, maybe that is up. Let me keep it up. Okay, then you have OpenCV, Mask CNN, YOLO models. All these are object detection models that exist. For our training for today and tomorrow, we will talk about multi-layered perceptron. We'll talk about CNN, only this part, not the other three, which is, we won't get into pre-training and all that. Then we'll also talk about recurrent neural network, RNN, only this part. We won't get into bidirectional, deep bidirectional and all that. This is the idea. Before that, of course, you'll have machine learning primer, deep learning primer, perceptron algorithm, etc. So that you get thorough understanding. And this understanding of deep learning primer and machine learning primer will help you immensely to understand all the other algorithms in deep learning, like CNNs, RNNs, etc. You will understand everything. It's very thorough. Okay, anything else now? And a few very interesting things happening in the space of deep learning are these two: GANs and reinforcement learning or QNLs. Amazing algorithms. Automatically they generate images, GANs. Automatically, I mean, just type the name, it will come up with an image. Elephant, it will come up with an elephant image. It will draw, it will generate elephant image. Or you can say artificial intelligence. It will write topics automatically on artificial intelligence. Movie script similar to Bahubali, if you type. it is going to come up with the movie script also. A lot of amazing use cases are happening on that front. Then you have Q learning, which is a part of which is an algorithm and reinforcement learning. Like you have supervised learning, in which you have regression techniques, decision tree, random forest, etc. In that way, you have reinforcement learning, in which you have Q learning, which is very widely used, very, very widely used. You have deep Q learning and all that. And this Q learning is used especially in gaming industry. What happens in gaming industry? You'll have a lot of options. If you are playing, say, Mario, Super Mario, that's a game, so a few of you all remember. How should that particular, Mario is a small cartoon character who is a hero of that show, and you are supposed to cross multiple levels, jump on a building, jump on animals, kill someone, so on and so forth. That's about your Super Mario. So your Q learning can automate that entire process. So take example of chess game. Chess. A lot of you are aware of chess. You need not teach Q learning algorithm on how to play chess. You need not say that you have a pawn, soldier. You can move only by one step forward. You need not teach. It will automatically learn. All you need to tell is maximize the score or minimize the score, whatever is your objective, and then it will learn and it will do everything on its own. I'll just play that video for you guys of Q learning for you guys to get some sense on what I'm talking about, right? So I'll see reinforcement learning. You'll have to just excuse me for a minute. I'll play this. Please keep watching this video. Come on. Yes. Just watch this. There won't be any audio. So it is digging a tunnel on this side. It's digging a tunnel here. So nothing was given to it as an input, friends. Absolutely nothing. It could learn just based on maximizing the score. If you just say maximize the score, that's it. With this objective in mind that it has to maximize the number of points or score, it plays the game. Okay, here are a few AI applications. AI applications are used to create videos, but it is also being used in a negative sense, such as, pornography is what people are, pornography videos is what people are generating using celebrity faces. Wrong thing. But yeah, AI is not always used in a positive sense, right? It is also used in a negative way. Then it is used in the travel industry. It is used in this specific scenario where automatically you recognize the faces of the people and only allow them enter your wedding. You invite people for your wedding. A few people come without your invitation card. Why embarrass them, right? Only, if their face is recognized that that person is a right guest, you allow. Otherwise, don't allow. Europe has its own AI strategy in place. It's pumping in money into research. So are the various other countries. Okay, AI is used in healthcare. AI is used in cybercrime. Okay, for ensuring that it safeguards your data. And the number of deals which were happening, number of mergers, acquisitions. If you are an AI-based company, people are acquiring you. Okay, so the number of such acquisitions, mergers, etc., increased tremendously. This is only data until 2017. You have 18, 19, 20, 21, 22. So things have just blown away. The number of research related articles which people are publishing, in that Microsoft leads the race, followed by Google and then IBM. People take huge pride. In automotive, maybe Tesla, etc., it is being used. Semiconductor devices are becoming very famous because your deep learning algorithms usually run on GPUs. So you have something called as CPUs, computing processing units, which we all are using on our computers. But then came something called as graphical processing units, which are at least, 20, 30 times faster than your CPUs. In some cases, GPUs are 100 times faster than your CPUs. Then people came up with tensor processing units, which are 10 times faster than your GPUs, graphical processing units. Enhancements in terms of the semiconductors, the chips that are used to run AI applications is increasing. And a lot of acquisitions have happened in the space of data. What do I mean by that? See, LinkedIn. LinkedIn is nowhere related to any AI, etc. But though they do some kind of recommendation engine, etc. Earlier, it wasn't extensively into that, but they were generating data of you and me, which company we work, what is our experience, right? What are the various companies we have worked with? Everything is captured. And Microsoft has acquired LinkedIn for $26.2 billion just because they have data. Okay, Intel has acquired Mobileye. Mobileye is an Israeli company. Do you know what they used to do? On the cars that you drive, they put a camera on the front. Okay, and then they make you use that particular camera, and they say that you can store your videos for free on my cloud. What do? You just enable your webcam or your dash cam, and then you drive. If you meet with an accident, all the proof is recorded on whether it is your mistake or the mistake of another person. So you can go to police, you can file a complaint with proof, you can give it to insurance company and claim insurance with proof. But what was happening is Mobileye was capturing the data. What kind of data were they capturing? They were capturing maps, street view maps, which a lot of companies such as Google, Waze, etc. use in their Google Maps, Waze Maps, etc. In that way, WhatsApp also, do they charge us? No, but nothing comes for free, right? So there is a lot of data which is getting collected by Facebook, and they're eventually using WhatsApp for business, etc. Many things are happening in terms of analytics. $22 billion is what Facebook has spent to acquire WhatsApp. So data. If you have access to data, you become rich. Simple. Then in detecting forgeries, like you sign on behalf of your father, if you get less score, right, on your report cards, maybe you did it in the past. Hopefully you're not doing it now. And on the checks, people try to forge the signatures that can be captured using AI. Cloud computing is a big thing which is happening, and a lot of AI is happening on cloud now. And that is the reason why we are conducting machine learning on cloud sessions starting from Monday onwards, which is going to be 6th June, of course, 22, right? It'll be from 6:30 p.m. to 7:30 p.m. Where can you watch it? YouTube. You go to, we'll also post the YouTube link. Okay, I thought I'll put it on my YouTube channel and then run it on that rather than interfere it with existing 360 channel. So I'll let you know. We'll post on the group and then you can leverage it. IBM is using it. AI facial recognition softwares are built by Hong Kong for law enforcement. It is used in asset management, real estate, right? A lot of companies are devising, AI strategies, so on and so forth. I mean, the list will go on and on. Border, country border, India, Pakistan, for example, border is patrolled. It is controlled on whether unknown person is there at the border or not, at the fence or not. Is he a potential suspect? All those kind of things. So bunch of things are there. Rather than I go through this, I leave it for you guys to read it. These slides would be made available to you all on your learning management system, AI Sprite. Please go to that. Okay. So I've just paused the screen share because I need to switch the gates now and get into something called as machine learning primer. Welcome to this. Enough of fancy stuff that we have done. Now we need to spend our time on understanding a few interesting things. Doesn't mean now whatever I'm going to talk would be uninteresting. This will also be interesting. Okay, and also after every 1 hour, we'll take 5 minutes break. 1 hour, 15 minutes, etc. So what is machine learning and how is it different to traditional programming? Okay, let us understand this part. Why did I do that? Pen, which I like the most. Okay. So in traditional programming, data would be given to you. When I say data, whatever is the historical data that you have. Maybe you have age as one column, gender, income, so on and so forth, different inputs. Or you can also have output variable in your data set. Output variables are denoted using Y. And input variables are denoted using X. You have data. And you write a program to get an output. I would rather not write it here. I would say this is another input. And you write some program to get an output. This is what traditional programming does. Take the data, write a program to get an output. But machine learning differs. Machine learning is slightly different. What happens when it comes to machine learning is you'll have data and you'll also have output variable. That means you'll have your variables, or think about from machine learning standpoint that you'll have inputs x1, x2, x3, x4, x5, etc. And then say you have an output variable. And then what happens is the computer will automatically come up with a program which can then be used for prediction purpose. Meaning it will automatically try to understand the relationship between the output variable and the input variables and it will try to come up with a program. If you use regression techniques, it comes up with a program which will help you formulate an equation like this. X1 is beta 2x2 plus beta 3x3 plus beta 4x4 plus beta 5x1. In this way, it comes up with a program. If you use neural networks, if you use deep learning algorithms like neural networks, then you get an equation like this. W1 x1 W2 x2 plus W3 x3 plus W5 x5 in that way. Why am I writing 5 W's? Because you have 5 inputs. And all of these are called as coefficient values or parameters or weights or estimates. These are all the various names which are provided to all these things. And this specifically beta naught is given a special name called as intercept or a constant. Intercept or a constant. Specifically, it is given a name. But this is also called as a coefficient value or parameter or a weight or an estimate, different names. On similar lines, this B, W1, W2, W3, W4, W5, all these are also called as coefficient values or parameters or weights or estimates. Similar to this beta naught, which is given a special name called as intercept or constant, within deep learning neural networks, deep learning or neural networks mean the same. This B is given a special name called as bias. It is given a special name called as bias. These weights or coefficient values or parameters or estimates, whatever names you want to give, are given as output. The program that we are talking about is nothing but these coefficient values. When you supply your data and output to your computer, a machine learning algorithm will help you come up with a program. Program is nothing but these coefficient values or weights or parameters or estimates, whatever you want to call, you can call. This is a key difference between your traditional programming versus machine learning. In machine learning, don't worry about, the program. You have data output, automatically your machine learning algorithm will give you an output, which is nothing but program. Program is these coefficient values or weights, which will then be used for future prediction. All the machine learning algorithms on the planet do exactly this. Take the data, try to establish the patterns, try to establish the relationship between your inputs and output. That is all it does. Underneath, different algorithms have different math way of capturing that relationship, but otherwise at a high level, that is exactly what it does. All right. Data is very crude, right? Raw data, some Excel sheet, etc. You try to get some information from that data. Information gives you knowledge, and on that knowledge, you take actions. That's wisdom. This is called as DIKW pyramid. And this is a stage which your algorithms have to help you move. From the raw data, bring out meaningful insights on which your decision makers can take decisions. Okay. There are a lot of machine learning type sprints, but at a high level, these are a few things that you should be concerned about. Supervised learning, unsupervised learning, reinforcement learning, semi-supervised learning, active learning, transfer learning, structured prediction, so on and so forth. In supervised learning, in the historical data that you're going to handle or the historical data that you're going to deal with, you will have output variable and input variables. Okay. Once you have your output variable in picture, it would be called as supervised learning, meaning you will predict that output. Who is the employee who will resign? Can I predict that? Yes. You can predict based on the age, based on the cadre, mean what position, manager cadre or vice president cadre, what is that cadre that this guy holds. Then based on income, based on appraisal, based on various other parameters, you can predict whether a person will resign or not, or treat or not. When you have this kind of data where you have output variable and where you need to predict that given the inputs, that is called as supervised learning. Within supervised learning, you can have classification problem or regression problem or recommendation problem or retrieval problem. These are the 4 problems that we'll have predominantly. Of course, now we have graph data and all that, but primarily this. If you want to predict whether a person will resign or not, or treat or not, it's called as 2-class classification problem, because there are only 2 classes. Will a person resign or not? If I give you images, and if I want you to classify whether someone is trying to shop, or is someone trying to steal, or is someone just trying to spend time in the shopping mall? There are 3 classes. Is someone going to buy your product shopping, or is someone trying to steal, or is someone just going to spend some time in your shopping mall? There are 3 classes, right? The moment you have more than 2 classes, it is called as multi-class classification problem. If you're trying to predict, say, salaries of people, you all are undergoing data science training and AI training, right? After your training, what will be your salary? Interesting problem to solve, I think, right? Salaries are, very important for a lot of people. Money is honey. Okay, but process is important. Just follow your process. Salary will automatically fall on the plate. The process is hard work and discipline. Okay. So regression, if you're trying to predict salary of people who have done their data science training, etc., then the output variable is numeric value, some number. In that case, it's called as a regression problem, or sometimes it's also called as prediction problem. It's called as prediction problem. Because in regression, you have something called as linear regression, and you also have logistic regression. If you have numeric value, only linear regression can be applied, not logistic. Okay, so anyways, so that's the reason why usually this predicting a numerical value is also called as prediction problem. Then you have recommendation. When you search for a product on Amazon or Flipkart or any other forum, then it will recommend you a few things. If you watch a YouTube video, it will recommend a few other YouTube videos. Right? That's recommendation problem. Retrieval means simple Google search. When you search reinforcement learning, what does Google do? It will look at the entire universe of documents it has and the websites it has, and it's going to retrieve only the most relevant documents. That's called as a retrieval problem. And then you also have unsupervised learning. Within unsupervised learning, in the historical data, you will not have your output variable. You will only have your variables, inputs, no output. Here, the objective will be like if I have all the customers of a bank, I want to maybe do a cluster that these are all the early adopters. Early adopters meaning these are the people who might want to purchase your new iPhone if you're going to launch it. Okay, or you'll have maybe student community. Maybe you'll have bridge customers. Bridge customers means those customers who are planning to purchase iPhone, but they need some push, some incentive, some discount. So when you have data, when you're trying to come up with these kind of patterns in your data, where prediction is not the objective, then it's called as unsupervised learning. Sometimes, even if you have an output variable in the data set, you convert that into an input. You treat it as an input variable and perform unsupervised learning. This is also something that you can do. Okay. Then you have reinforcement learning. We have already seen this. Reinforcement learning, I'll give you yet another example of stock market. On stock market, you have Infosys, TCS, Wipro, HCL, so on and so forth. You have a bunch of companies, right? Which company stock should I purchase? And how many shares should I purchase? How many shares should I sell off? How many shares of a specific company should I hold? So you'll need to understand that on stock market, you buy, you sell, and you hold. You sell a few stocks, buy a few you hold. There'll be thousands of companies which are trading on stock market. Which one should I buy? How much should I buy? Which company stocks should I sell? How much should I sell? Which company stocks should I hold on to? Huge number of decisions to be made. When you have huge number of decisions to be made, you use something called as reinforcement learning. Your algorithm will automatically identify all the various patterns across the various companies. You know, if I sell, hold, buy, how many should I sell of which company? How many should I buy of which company? How many should I hold on to of which company? All these decisions are automatically learned. The only thing is you need to mention that my objective is to maximize return on investment. Maximize my returns. Maybe you spent $100,000. So for the $100,000 I've invested in the stock market, how much will I get? How much can I potentially get if I invest in stock market? Maximize those returns. And your reinforcement learning algorithms will automatically identify all those patterns and give it to you. You need not worry because huge number of decisions to be made here. Humanly, it is not possible. Even for your traditional machine learning algorithms, it's not possible. Here, there should be some other different way of analyzing, and that's called as reinforcement learning. Okay. Then you have semi-supervised learning. it combines both supervised and unsupervised. There are two ways to look at it. One way is you take your data. Okay, you have, say, your output variable and input variables. You take these and you start treating your output variable as another input and perform unsupervised learning on that. So perform unsupervised learning. What, say you want to perform clustering or segmentation. And then you come up with different clusters, cluster 1, cluster 2, cluster 3. Okay, in this cluster 1, you'll have some data. Cluster 2 also you'll have some data. And in cluster 3, also you have some data. Okay. And then what you do is you take this data set and apply some supervised learning algorithm on that, supervised learning. Maybe you want to apply linear regression. Okay, maybe on this data set you want to apply maybe decision tree. Maybe on this data set you want to apply neural network algorithm. So what are you doing? You're first applying clustering technique, which is unsupervised. On top of that, you're building your predictive modeling techniques, which is supervised. You're combining both. When you combine both, it is called as semi-supervised learning. Then there is yet another way of looking at this semi-supervised learning, and that is, suppose you have images, radiology images. Okay, suppose you have a radiology image. What do you mean by radiology images? Let me show you if I can probably from here. Yeah, these are radiology images. This is breast related thing wherein we wanted to predict breast cancer. And these white dark spots are called as calcium deposits, calcification. So these calcium deposits can cause tumor or they might not cause tumor. We don't know. All these are images. You have MLO images, you'll have various other images. I'll not get into that. These are the various classes. Given an image, you need to classify whether that image is benign or malignant. Benign means benign means cancerous, I believe. Malignant is non-cancerous, or the other way around. Why did I forget? Oh my God. This is called as blackout. Just give me a minute. Let me quickly do it. Okay, benign means non-cancerous. Okay, benign means non-cancerous. Sorry, friends. I worked on that project. I keep doing it day in, day out. Sometimes I just black out. Okay. So we have these many classes. Given an image, you need to classify whether it is dense benign calcification or dense malignant calcification. Is it dense normal or is it dense malignant or fatty normal, fatty suspicious, so on and so forth, multiple classes. Usually, when you collect this data from hospitals, they won't give you the label. They'll just give you the images. They won't say, hey, this is fatty malignant, this is dense benign. They won't classify and give you. They'll just give you the images. And in order to give labels for each and every image, you need to say whether it is benign or malignant, etc. Right? If you want to do that, you will not have knowledge, first of all. By looking at that image, how can you conclude whether it is cancerous or not? So what should we do then? You'll hire a radiologist. Radiologist means person who has done MBBS plus specialization in radiology. master's in radiology, it's a very costly thing. They will charge you a lot. For every, to analyze every image, it takes at least 10 to 15 minutes. And for each hour, they charge you some 10,000 or so. So even if it is 3,000 images that you want to label, it will be very, very costly. So what you can do is apply semi-supervised learning technique. Means what? Suppose you have a data set wherein you have, say, 3,000 images in your data set. You have the image, which is nothing but your input, and you have the label, which is nothing but output. So maybe you will come up with a decision that, do you know what? We don't have the money to pay such huge amount to the radiologist. So we will make the radiologist look at the first 500 images and give labels to that. This is benign, this is fatty malignant, this is suspicious, so on and so forth. For 500 images, you'll ask them to come up with labels. And you'll use this data and you'll build a model. Okay? You build machine learning model on that. Once you have the model, from 501 images onwards, you just give the image to the algorithm that you built, and this model will give you the output, which is nothing but label. So you take that label, you put it here. In that way, what you're going to do is you're going to make use of those images where you have labels, or that data where you have output variable, and you build a model to predict on that data where you don't have output or where you don't have label. This way you're saving money and you're saving time. Labeling all these things, even if a radiologist takes 10 minutes to analyze each image and give a label, that's costly, time consuming, and also costly. You get rid of those two by simply doing this. This is also called as semi-supervised learning. So semi-supervised learning has two definitions. One is this, another is you apply some unsupervised learning and then apply supervised on top, or use combination of these two. Then also it's called as semi-supervised. In unsupervised learning algorithm, you will not have output variable. On this data, do you have output variable? No. So you're taking that data and then using your model to predict the label. When it comes to supervised, output variable is known. Okay. I'll get to that. Okay. Active learning or transfer learning more or less means the same. What does that mean? Suppose I built a model on cats and dogs. Okay, what do you mean by building a model on cats and dogs? Okay. So you have images. You have cat images, you have dog images and all that. And then by looking at that image, you need to classify and give a label on whether it's a cat or a dog. Okay, so you'll have images. And for each of that image, you have to say whether it is a cat or a dog, etc. And then you build a model. Building a model means what in neural network? Just coming up with that equation. W1x1 plus W2x2 plus W3x3 plus W4x4, etc. Once you come up with that equation, you use that equation for predicting. Now, can I use the same model and apply it on different data set wherein I have cancer images, radiology images, DICOM images, X-ray images, whatever you want to call it. Let's say you have those images. Can I apply the same model on this and try to classify whether the image is benign or malignant. You're talking about a data set where you have built a model to classify whether an image is cat or a dog. And you're saying on another side, you have images which are radiology images. Can I do it? Absolutely, you can use it. Absolutely, you can do it. And that is called as transfer learning or active learning. You call this as making use of pre-trained models. You build a model, you save it and call it as a pre-trained model, and you reuse this pre-trained model on a different objective altogether. Wow. Yes, and that's something that you learn as part of CNN. Okay. All right. Then you have structured prediction. Wherever you have series, a sequence of words, right? Sequence of music tone, genome sequence, your gene in pharmaceutical or life sciences, basically. You call it as genome therapy, etc. Right? Where people understand your gene sequence, your DNA sequence. In those kind of scenarios also, if you use any predictions, it's called as structured prediction. So these are the various things we have, and a lot of additional things exist. But I think I need to now look at the questions. There was one question from our friend. Okay. In semi-supervised learning, my dear friends, think about a data set wherein you have different customers, customer one, customer two. Say a specific bank has 10,000 different customers. Say you have age of a person, gender of a person, income of the person, so on and so forth. And I have new iPhone, which is launched in the market. And I want to do email marketing. Since I have 10,000 customers, should I send this email that there is a special 10% discount on iPhone if you purchase using my bank credit card? If you use, say, for example, HSBC credit card, then should I send it to all 100,000 customers? If I have 100,000 customers, should I send it to everyone? If I send it to everyone, I'm unnecessarily sending this email to those customers who might not even be concerned about 10% discount. If I say that Virat Kohli, there is 10% discount on iPhone, to Nadal, tennis star, will that person be interested? If I send it to Joe Biden, US president, that, hey, that's 10% discount, would that be making sense? No. Even worse, what they might do is they might select your email and click on spam, or they might unsubscribe. So the future emails which are relevant also will not reach them. Hence, what you do is you do clustering or segmentation. You do segmentation or clustering, where maybe you'll come to know that, hey, these are a bunch of affluent people. Affluent means wealthy people, well connected. Maybe you send them, it might work out. Or maybe it might not work out. Maybe there'll be bridge customers who are like, I want to buy iPhone, but I wish there was some discount. So this kind of segment is very, very relevant for your email. So maybe you should only send it to them, not to everyone. That's where unsupervised learning comes into picture, which will help you perform segmentation. Or clustering is one of the techniques. Here, there is no prediction happening, right? So there's no output variable. Okay. Tariq. Okay. Tariq Anwar. If you're there still, let me see whether time. Okay. Yeah. All right. So these are the, I will take a break in the next 2 to 3 minutes, friends. Just give me 3 minutes time. Output variable has different names in different books. When you talk in the interviews, different interviewer might have different term. I mean, they might use different terms in their companies. They might say simply, okay, explain about your project. When you keep explaining about your project, they might say, what was your explained variable? Or they might say, what was your experimental variable? Or they might use a term, what was your regressand? You should not be like, oh, I don't know those terms. Here they are, learn. Right? Response variable, dependent variable, regressand variable, explain variable, criterion, measures variable. All these mean output variables simply. And your input variable also has different names. Explanatory variable, predictor variable, independent variable, covariates, regressors, factors, carriers, controlled variable, manipulated exposure input. All these are the different names given to input variables. It is always better for us to understand and internalize the different terms, different names. It is beneficial from interview standpoint also. Okay, after this, we'll quickly take a break. So if there are images and if you are supposed to classify whether that image is cancerous or not, what problem is it? Is it classification problem, or is it regression problem, or recommendation problem, or retrieval problem? This is all you need to tell me. Okay, which problem is this, friends? Everyone. Classification problem, because you're classifying whether it is benign or malignant. How many class problem is this? Is it multi-class problem or two class? Yes, it is two class classification. What will be the stock value tomorrow? What problem is this? Stock value is prediction. It's a number that you predict. What will be your stock value is a number that you predict, numerical value. So it is a regression problem or prediction problem. How much interest rate should I lend money to a specific customer? What problem is this? Number, right? Interest rate is a number. So it is called as prediction problem. Will employee attreat or not? Attreat means resign. Will an employee resign or not? What problem is that? Classification. How many class problem is this? This is two class classification problem. Whether a person will attreat or not, resign or not, is two, only two you have. Hence it's called as two. If I give you a video and ask you to check whether a person is shopping or stealing, what problem is that? Classification, you're classifying. And how many classes do you have here? Two, stealing or shopping. So it's a two class. Okay, if you're given an image and if you're asked to classify whether you have a man or a woman or an animal in that particular image, what do you call? Classification problem. But since you have more than two classes, you don't have two, more than two is what you have, then it's called as multi-class classification problem. How many MacBook Pro am I going to sell? What problem is this? Prediction. It's a prediction or regression problem. Right? Prediction or regression. But it's new number. Number means prediction. Okay. You have a tweet which you post on Twitter. Now that Elon Musk is has taken over Twitter, it becomes even more interesting. Let's see. So if you want to classify a tweet as positive or negative, then what problem is this? Classification. And how many classes do you have? 2. You usually classify whether a tweet is positive or negative. So it's a 2-class classification problem. Think and answer. Think and answer to this question. Which song are you humming the tune of? You don't remember the lyrics. You're just humming the song. You're humming some song. Then what should it do? Based on your humming, it should look into the database, which has bunch of songs, and it should pull out the right song. It should pull out the right song, the tune of which you're humming. Retrieval problem, friends. You have a database full of songs. You don't know the lyrics. So what are you doing? You're humming the song. And based on that, it will retrieve the right song and show it to you. It's like a Google search. You're searching, it will give the relevant songs. Okay, say you invested in real estate on land. How much will be the cost of that after a decade? What problem is this? Number, right? You're talking about how much will be the price. Number. If you're talking about number, it is prediction problem. Then, say you're planning to get married because you cannot afford to stay happy always. So in this case, say you went to a marriage website, matrimonial website, and then you're searching for your soul partner, or you went onto a dating website, you want to date someone. What will it give you? Some details of someone. But what is it going to do? Based on your likes and dislikes, it's going to recommend, right? It is going to recommend who are those people with whom you are going to be happy throughout your life. People who know me know that I'm being sarcastic here, but nevertheless, right? Okay, we are done with the memory check. Now, what's the time? I think we need to take a quick break, then discuss about a few other things, and then we'll talk about a few additional things and jump into deep learning. So now is the right time, I think, for us to take a quick break and get back. So let me pause the recording as well. All right. So I just changed my webcam position so that you can see me clearly. Maybe I wasn't visible on this side. Okay, friends, so let's proceed further. CRISP-DM is a project management methodology to handle your data science projects. We also have something called as CRISP-MLQ, which is now extensively being used. ML stands for machine learning. And Q stands for quality assurance. Okay, and CRISP-DM and CRISP-MLQ, both of these have 6 different phases. Both of these have 6 phases. 6 phases. And CRISP-DM, these are the 6 phases, right? Within CRISP-MLQ, these 2 phases are combined into phase 1. Then you have data preparation, modeling, evaluation, deployment, and you have another phase, which is called as model monitoring and deployment. This is phase 6. These are the 6 phases that we have. Okay. Whenever you have data, historical data which is given to you, you draw the insights from that data. Whatever data you have, based on that, extract the insights. Then use your domain knowledge, use your experience of the industry or the domain that you're working with, and then come up with new features. You come up with new features, new variables. And once you have new variables and features, then you combine them with the existing data. You have your data, okay? You come up with new features, combine them, and then build your model. Once you build your model, you use your model for doing predictions. Based on the prediction output, okay, based on the prediction output, you actually take decisions. Here is a decision. Whatever decision you take should help you meet your business objectives. Maybe you want to minimize the loan defaulters, or maybe you want to maximize the agriculture yield of the crop. Whatever be the objective, you need to meet that. Given the constraints, constraints are limitations which always would be there on you. Okay, it's kind of probably recap, because as part of Crisp ML, we would have already given you training on these things. But then what happens is, after the decision is taken, you get a feedback, whether that's a right prediction or wrong prediction. Say, for example, this is a loan default prediction model. One of my classic examples. If your prediction says that this person will not default, then what do? You usually approve the loan. Once you approve the loan, after a few months, after a few installments, installment 1, installment 2, installment 3, and then say the person defaults. Defaults means doesn't pay the loan, absconds. Then that is a feedback that you take, that, you know what, our model has predicted that people of this kind will not default, but in reality, this person has defaulted. If in reality the person has defaulted, then you need to add it to your data and then retrain the model. This process will go on and on. Okay. Over a period of time, your model will mature in terms of accuracy. Initially, when you build the model, maybe it might give you an accuracy of 80%. Then as and how you start retraining your model might give you an accuracy of maybe 90%, right? So eventually your model accuracy will increase. Here, this is an example of drone. You fly drone on top of the agriculture crop and you detect wherever there are insects. Using image processing, you'll have something called as multispectral cameras to this drone, right? You attach multispectral cameras. Multispectral cameras can capture ultraviolet spectrum and infrared spectrum, and both of these are invisible spectrums. Invisible to human eyes. You cannot see, because an insect on a nice green crop will be in green color. With naked eye, you cannot find out. But these multispectral cameras will capture the heat being emitted. The plant and insect will emit different heat. Using that, different heat map gets generated. Using that, you can figure out whether that's an insect or not. And then You sprinkle pesticides. You sprinkle pesticides exactly on that insect and kill only that. So you don't waste your pesticide. You don't sprinkle it on healthy plants. If you sprinkle excessive pesticides, it will go into the soil. And next time when you come up with a new crop for 6 months, again after 6 months, you put a different crop. When you do that, if you have residuals of pesticides, etc., in the soil, yield will not be better. Yield in the sense next crop won't give you good results. So your drone driven technology, drones are also called as UAVs, right? Unmanned aerial vehicles. These are becoming very, very famous new field of, this is one of the most sought after fields when it comes to AI experts. As AI experts, people are preferring this. Self-driving cars are also part of UAVs. Okay. Anyways, that would capture the data, right? And it will sprinkle pesticide exactly on that insect so as to kill that. Here, the objective is to increase the yield, maximize the yield. And the constraint is to minimize the cost. You cannot say that I'll give you a drone with multispectral cameras, contour sensors, right? All of that doesn't help because it has to be also cost effective. Okay, recommender engine and then credit card default, loan default, all these things follow the same process. You take your data, you come up with new features using your domain knowledge, use your data and new features and build the model. But this part would be called as predictive modeling. You're also expected to perform exploratory data analysis or descriptive analytics, which is part of drawing your insights and then to take a decision on that. And always when you take a decision, you feedback. Take the feedback, add that to the data. If it's right prediction, wonderful. If it's an incorrect prediction, then you need to retrain your model. And when it comes to data, you have structured data and unstructured data. Within structured, you might have big or not big data. Unstructured also might have big or not big data. If you have structured big data or unstructured big data, you end up using Hadoop framework. Either it is structured or unstructured. If you have big data, use Hadoop framework. If it is structured and not big data, use MySQL or some relational database management systems. PostgreSQL databases or Microsoft SQL or Oracle database. If it is unstructured, not big data, you might want to use MongoDB, which is a NoSQL database. All this knowledge is very, very important when you work on projects, my dear friends. When you talk to your interviewers in interview, first question will be, explain about your project. All these things are important. If you have worked on project, you should understand whether the data that you were dealing with was big data or not big data, right? Whether it was structured or unstructured, or was it something to do with time series data, or was it related to graph data, network analytics? These are things that you need to talk about. Okay. Okay, these are a few things that I highly recommend you guys to remember. Row or instance or record or case or example or sample, all these mean the same, or observations, all mean the same. A column in your data set is also called as attribute, feature, variable, etc. In these columns or attributes or features or variables, you also have class or outcome variable. Output variable is given a special name. These are all your traditional algorithms. When it comes to supervised, these are the various traditional algorithms. When it comes to unsupervised, these are the various techniques that you have. When it comes to time series, these are the various techniques that we have. I'll just strike off these just to ensure that all the other algorithms that are there are your traditional algorithms. These algorithms are used when it comes to supervised learning. These are used when it comes to unsupervised. These are used when it comes to time series. Okay, next. What if you have multiple outputs to be predicted at one go? You have multiple outputs and immediately you want to predict. Okay, then you need to use certain advanced techniques. Usually, when it comes to predicting multiple outputs at the same time, we use functional APIs. Functional APIs of your deep learning library, which is Keras. Within Keras, you have something called as functional API that can be used, which at one go will predict multiple outputs. Okay, can you give me an example? Sure. So suppose you have Twitter tweet. Someone has tweeted on the Twitter. Say using this tweet, you want to know what might be the appropriate or approximate age of the person, what might be the gender of the person, and approximately in which year did that person tweet. Can I classify or can I predict all these three? Yes, you can. From the tweet, you can get all these things. Or maybe what was the age of the person, gender, and what is the sentiment? Was it positive or negative? Did a person tweet positively or negatively about some subject? These things can be done. When it comes to deep learning, neural networks, these are the various algorithms which are part of supervised learning. Perceptron algorithm, multi-layered perceptron, convolution neural network, recurrent neural network, long short-term memory, gated recurrent neural network, etc. So on and so forth. And to this, there are a few other things which are added, which is transformers. Okay, you have BERT, you have GPT, so on and so forth. And then on the other side, when it comes to unsupervised learning, you have autoencoders, RBMs. RBMs and DBMs, restricted Boltzmann machines, and this are not widely used nowadays. I would say not used, but just for your understanding, I've kept there. GANs, obviously. Reinforcement learning, which is a different subject altogether, is also something that is worth discussing. Like you have supervised learning, unsupervised learning, there is another thing which is called as reinforcement learning. And within that, you have something called as Q learning. And then when it comes to time series data, you can use your RNN and variants. RNN, LSTMs, GRUs, etc. can be used when you have time series data. And there's something called as Ellman and Jordan neural network. Bunch of things. Okay. A lot of other things are there. And when it comes to object detection, detecting what is there in the object, you have mask, RCNN, region convolution neural network. Then you have YOLO models. You only look once, YOLO models. All these are amazing models when it comes to object detection. Given an image, detect what are the various objects. Very, very useful when it comes to self-driving cars, or very, very useful when you have unmanned aerial vehicles, drones, driverless cars, etc. Okay, this I should skip. Certain things, friends, I think it makes sense for me to skip. Certain things we can talk about. I just pause the screen, do not worry. I'm just figuring out on what are the various things that I need to cover. Makes sense maybe, but at a high level, I'll just proceed further. What if you do not have the data that is required for performing modeling? What do? I don't have the data which is needed to build model. In that case, what do you do? What should you ideally do? You need to perform data collection. You need to resort to primary data collection mechanism. Primary data collection mechanism includes conducting surveys, conducting experiments. Those are called as designing your experiments, design of experiments. You might want to perform simulations. All these are the various ways of generating data. Okay. What if you have noise in the data? Remove it. Save outliers. You have special characters. When you analyze the Twitter tweets, you might have emoticons like this, a smiley, or someone might be crying. You will have a lot of emoticons. Remove it. That's all noise. What if you have outliers? Deal with the outliers. There is a technique called as 3R technique. Deal with that. Winsorization or trimming or clustering, right? Or 3R technique wherein you rearrange, rectify, or remove the outlier or retain the outlier, right? Winsorization, trimming are the different other techniques. What if you have 100,000 outliers out of 100 million records? What do you do then? 100 million records, huge data set, and 100,000 outliers. Can you humanly analyze each and every outlier? No. What do you do then? You create clusters. Probably if you have a box plot like this, you might have outliers here and you might have outliers here. Treat all these outliers as one data set. Treat all these outliers as data set, another data set. And the remaining data will become the third data set. What if you have missing values? You perform something called as imputation. What if you have duplicate data? Remove the duplicates. Why do you need duplicate data? See, for example, if you have a data set, in which you have an output variable and 3 inputs. Say the output is person will default on the loan, age is 23 years, gender is male, and education is graduate. They have various rows observation. And another row is also person will default, age 23, male, graduate. What does any predictive model do? It will understand the patterns between output variable and input variables, right? Any machine learning or predictive modeling technique will do the same to try to establish the patterns between your output variable and input variables. That is all it does. Then, if a person is 23 years old, male, and graduate, person will default. It learned that pattern. Your algorithm has learned that pattern. If you have another row, which is exactly the same, 23 years, male, graduate, how does it help? Person will default. Already in this observation, your model has learned that pattern. If you're giving the same pattern again, doesn't help because model already learned this pattern once. Hence, duplicates doesn't make sense. So when you have duplicates, remove the duplicates. Usually duplicates do not make sense. What if you have non-normal data? Yeah, what do you do? Friends, very, very important thing. I mean, I keep coming across this specific question on why do you, a lot of people ask me, and on why do you even worry about, duplicates? Oh, sorry, non-normal data. What if your data is not normal? This question a lot of people have asked. So, one second. Friends, in the good old days, when people have come up with machine learning algorithms, they assume that a lot of things were normal. They assume that the world is a normal place to live. Okay? Everything will be normal, etc. But then that wasn't the case very soon. And then in the good old days, when people started building or coming up with machine learning algorithms or statistical techniques, they assume that world is a normal place to live in. Now you and I understand world is very abnormal place to live in. Nothing is normal here, right? So when people assume that everything was normal, they build statistical models under the assumption of normality. They assume that things were normal. Based on that assumption, they came up with statistical models. Even today, those statistical models are very widely used, very useful. But it is based on this assumption that data are normal. So only if your data are normal, these statistical models will work well. Not that they won't work at all, they'll work, but they'll not work well. So if your underlying data is non-normal, income, a lot of people belong to weaker income group or middle income group. Only a few people fall in high income group, like Adanis of the world, Ambanis of the world, etc. They'll have, it's exponential. So world is non-normal, obviously. Income disparity is so high. In these kind of scenarios, if your underlying data are non-normal, if you supply it to the statistical model, it won't work. Why? Because the assumption of this is that data should be normal. So when your data are non-normal, you might want to do something called as transformation. And make your data normal. So non-normal data, here it is exponential, but non-normal. You try to do some transformations to make it normal. Once data becomes normal, and then if you apply statistical models, it works well. It gives you good results. But after transformation, if your data is still non-normal, there is no guarantee that this will become like this. There's no guarantee. Post-transformation. Post-transformation, it might still be the same. If post-transformation, if the underlying distribution is the same, then you need to proceed further with non-normal techniques. Like you have your neural networks, deep learning models, etc. All those can handle non-normal data. Okay, so now you also understand what you need to do if you have non-normal data. If you have heterogeneous data, not similar kind of data, very different data. For example, if you are conducting a survey and you have an 18 years old person who is giving you a reply or who is filling that survey, and also there is 60 years old person who's filling the survey. 18 years person, 60 years old. When you have data of these two people who have wide thought processes, obviously, then that is called as heterogeneous data. Your models won't really work well when you have heterogeneous data. That means wide, changes in the data. It's not similar kind of data, right? In that kind of scenario, it always makes sense for you to do clustering or segmentation. When you do clustering or segmentation, you get different segments, and then you work on each and every segment. All right. Sometimes you might have data which is daily data, daily sales data. Maybe you want to aggregate it and make it monthly sales. You have daily sales data. You want to make it monthly sales. So you have day 1, day 2, day 3, in that way, you have sales. For 30 days, if you add, it becomes monthly data. So you just add them, add all of these, and you get a single value, monthly sales data. That's called as doing aggregation. Based on your business requirements, you do that. Discretization is making continuous data into discrete. Then your feature selection. If you give me thousands of inputs or variables or features to work upon, it might be difficult. So I will select only the most important features. And in this feature selection, you have something called as RFE based technique. Okay. You also have lasso regression. You can use hypothesis testing. You can use your domain knowledge, common sense. And then you have decision tree information gain, which is very much part of decision tree. Then in random forest, you have something called as variable importance plot. And there are various other techniques. You have something called as Shapley values or Sharp values that also helps you select the most important features. So domain knowledge is more from business standpoint. Rest all are math-driven, statistics-driven techniques. This will help you figure out the most important features. Use only the important features in your analysis and job done. Okay. Then we have feature extraction. When it comes to feature extraction, you have manual way of extracting the features, and you have automatic way of extracting features. And manual way of extracting new features is one is principal component analysis. Or when it comes to images, you have something called as SIFT, SURF, OBrief, FAST, bunch of techniques. Or you can use your domain knowledge. Domain knowledge means if you have, say, latitude value and longitude value, if you have these two values, using these two, I can come up with a new variable which is called as location. Using latitude and longitude coordinates, you can come up with location. So using your domain knowledge, you can come up with new features. Okay. And then there is automatic way of dealing with it. So let me tell you, if you have less data and if you want to still build your machine learning algorithm, then manual way of extracting the features is better when you have less data. And manual way of extracting the features is important when it comes to traditional machine learning algorithms. Traditional machine learning algorithms. All these are interview. I mean, people can ask you questions from anywhere, friends, and I'm covering as many interview aspects as possible. So please pay attention. It is always better to attend these sessions or watch these sessions so that you understand all the aspects. Okay, and impress the interviewer, ask for more salary. I'm sure everyone wants better salary, better packages, better career, better life. Okay, so if you have less data, or if you're using traditional machine learning algorithms, obviously you resort to manual feature extraction. For example, if you are given an image, I cannot supply the image as is to my algorithm. What should I do? I should basically look at, I would basically look at how many rows and how many columns do we have, and that is called as pixels. In an image, it is called as pixels. Images have pixels, right? 1, 2, 3, 4, 5, 6, 7. So 7 columns. And how many rows? 1, 2, 3, 4, 5, 6, 7. So it is 7 by 7 image. 7 by 7 means you'll have 49 grid values. 49 grid values. And each grid value, each grid will have something called as pixel intensity. Pixel intensity. And pixel intensity values range from 0 to 255. 0 means black. 255 means white. Anything in between would be gray. Numbers which are close to 0 would be black. Numbers which are close to 255 will be white. And in between there'll be gray. I'm talking about a grayscale image, not a color image. So this is a data set that you have, which is a bunch of images. Feature extraction, if you want to do manually, then what you need to do is, you need to extract the pixel intensity value of each grid and put them into a database or into some CSV file or Excel file or some structured database. So you have X1, X2, X3. How many should you have in total? 49. Why 49? Because you have 49 pixels. So each pixel will have a value. Maybe first pixel here is extremely black, so it will be 0. Maybe this pixel is slightly black. Maybe it will have a value which is 70. In that way, you'll fill all the values for one image, second image, third image, for all the images have it. So what are you doing? You're manually extracting the features from images. Image is unstructured data set, right? Images are unstructured. So you're extracting and you're putting it into a table and you're making it structured. Unstructured data, you're manually converting into structure. Then you apply a machine learning algorithm on this or predictive modeling technique on this. Job done, right? If you have audio files in, as part of our professional certificate program in data science and AI, we also teach how to deal with audio files. And there's something called as MEL frequency substral coefficient, using which you can extract features from audio files also. Then if you have textual data, people usually use bag of words or a document term matrix in which you have term frequency or term frequency inverse document frequency. There are a bunch of techniques which exist. Okay, which will convert your unstructured data, which is textual data, into structured format. This is manual way of extracting. When do you do this? When you have less data, you extract manually the features, and on the structured data, you apply your machine learning algorithms. Traditional machine learning algorithms usually are applied. On another side, you have automatic way. When you have more data, when you have more features, when you have more observations, when you have images, when you have video files, when you have textual data, audio, where there is more complexity, then you usually end up using deep learning models, deep learning algorithms. Deep learning is synonymous with neural networks. And this will automatically extract the features. You might ask me, Barney, if there is automatic way, why should I resort to manual way? I told you already, if you have less data, your deep learning or neural network doesn't give you good results. Deep learning or neural network algorithms need more data. So if you have less data, yes, obviously manually you need to extract if you want good accuracy. If you have more data, yes, do this. However, business aspect comes into picture. Business aspects are that whatever features are automatically extracted, you don't know what those features are. So it will become black box. So there won't be any explainability. What do you mean by explainability? If you build a loan default model, and if your model predicts that a person will default on the loan, you reject the loan, right? If there is a person who applies for a loan, then you use your machine learning algorithm, and this algorithm will say that this guy will default. And based on that, you reject the loan. This person can come back to you and ask you, why did you reject the loan? If you use decision tree or linear regressions, linear regression or any of your regression techniques, you can answer to this person using the coefficient value, you can answer. But if you use deep learning algorithms, you cannot answer. If you cannot answer on why, if you say that, do you know what, I use deep learning algorithm, it's black box. I don't know, but you'll default, it seems, supposedly. If you use such an explanation, this person can sue you, can file a case against you in the court. And there are a lot of regulatory bodies, right? Like European Union, GDPR, General Data Protection Regulation Act. If you cannot explain him, they will sue you. You'll pay a big penalty. In those kind of scenarios, people still prefer traditional machine learning algorithms. And if you want explainability, as in this case that I explained, loan and person asking why you default rejected the loan, right? In these kind of scenarios, you need explainability. But when it comes to deep learning models, there is no explainability. Black box, unfortunately. Yeah, on one side, automatically features are extracted, but on another side, you don't know what those features are. So you use deep learning models in those scenarios where people don't demand for explainability. Places where people demand for explainability, still you need to go with your traditional machine learning algorithms. Okay, so feature extraction can happen manually or automatically. Just remember that. And there are a bunch of sampling techniques which exist. The most widely used is simple random sampling. Okay. Your data can be balanced or imbalanced. Okay. Meaning if you have your output variables and if you have various input variables, here you have default and non-default. And if you have, say, 10,000 observations, default, not default, if it is 50% default, 50% not default, it's balanced. 40%, 60% balanced. 30%, 70% is imbalanced. Sorry, balanced. Until here it is balanced, my bad. But if you have one of the classes less than like 29% default and 71% this, then you call this as imbalanced or unbalanced. But usually imbalanced is a term which is used. So when you use your, of course, okay, this is balanced and imbalanced. To handle your imbalanced data sets, usually you perform random resampling, that is undersampling or oversampling. Undersampling means default has only, say, 2,900 observations, which are default in this. Remaining 7,100 are not default. Then what you do is in undersampling, you ensure that you take 2,900 from here and only 2,900 from here. Undersampling, you're not taking everything, you're taking very less undersampling. Oversampling means maybe you ensure that in the sample that you get, you have more of default cases and less of not default cases when you sample. That is also more or less like this one, 2,900, 2,900. Right? Or maybe from 10,000 observations, you want only 2,000 observations to build your model. Assume. Then you'll ensure that you have 1,000 of this and 1,000 of this. Right? So what are you doing? You're in comparison to your not default case, you're trying to get more of default. Oversampling. Correct. Otherwise, what will happen? If you want this 2,000, ideally it will get split in this way. Means you'll have, suppose you want 1,000 observations, just for understanding. 29% means 290. 71% means 710. Ideally, it should split in this way, right? But what it does is it will oversample this. And it will ensure that you have approximately 500 of these and 500 of these. So wherever you have less, it will increase the count. Oversample. K-fold cross-validation, SMOT, modified SMOT, cluster-based techniques, ensemble techniques, bagging and boosting. In boosting, you have all these three. All of these majorly address your imbalanced data sets. Okay. If you automatically extract the features using neural networks, which is deep learning, explainability is gone. But what can you do? Don't use this then if explainability is important for you. But still, if you want to include explainability, bring in explainability, there are a few techniques such as GradCam, class activation maps. This you learn as part of your AI professional certificate program in data science and AI in detail. Generate heat maps and all that. And there are other techniques also. Okay. This part I'll just quickly touch upon. Suppose you are trying to predict whether there will be earthquake or no earthquake. If you predict that there will be earthquake, which is a positive case, it is a positive case. You're predicting that there will be earthquake. But in reality, there is no earthquake. Means it's a false prediction. Okay, earthquake, if you're going to have, it's positive case. Like you have COVID, means you're tested positive. No COVID means it's a negative case, correct? On similar lines, earthquake means it is positive. No earthquake is a negative case. If you're predicting that there will be earthquake, it's a positive case. But suppose there was no earthquake, then it's a false alarm, false positive. The moment you predict that there will be earthquake, what will people do? What will government do? Government is going to evacuate people, create makeshift camps so that it transports the people to that location, different location, to a safe location. Makeshift camps will be set up. Government might deploy armed forces to evacuate people. Offices might shut down and ask their employees to work from different locations. So business continuity plans will trigger. Many things will happen. And there is a cost associated with this. Say this is going to cost you $1 million. $1 million. But if it is a false alarm, you predict that there will be earthquake, but in reality there was no earthquake, then what will happen? You lose $1 million. Let's take the other case. No earthquake is a negative case. You predicted that there won't be any earthquake, which is a negative case. Negative. N for negative. P for positive. But then, in reality, there was an earthquake. You're predicting there won't be earthquake, but in reality, there was an earthquake. So this is a false alarm that you have given. You're telling to the government that there won't be earthquake, but there was earthquake. So false alarm is what you have given, false negative. Then what happens? If you say there won't be any earthquake, people will be relaxed. Suddenly there's earthquake, very high intensity on a richer scale. Then a lot of people are going to die. After that, if you deploy your armed forces, etc., what will happen? Only dead bodies, debris is what you will bring on. Huge loss, right? Say that loss of life, property, etc., turns out to be $10 million. Okay, so false negative is very costly, 10 million, and false positive is only 1 million. So what you do is, ideally, in your underlying data set, if you have one no earthquake example row, you're going to put 10 earthquake scenarios because you want your model to accurately predict your earthquake. So you have for every no earthquake, which is negative case, you're going to have 10 positive cases, 10 earthquake scenarios. Why did you do it in this way? Sampling, because that is how the cost is. Okay, false negative will give you 10 million, false positive, you lose 1 million. So you need to predict your earthquake correctly. So for every no earthquake, you're going to have 10 earthquake You'll have in the ratio of 1:10 because 1 million is to 10 million. This is very, very, very important. We should not always start thinking from, let me by heart all the algorithms, okay, decision tree, random forest, and all that, and I'll mechanically go and implement projects. No, no one will respect you if you mechanically do things. Apply your domain knowledge, apply your common sense, apply your business acumen, then do the projects. Then people will start loving you. They'll respect you. In interviews, you'll be regarded, very highly. Okay. Then you have feature engineering. When it comes to feature engineering, using the existing features, I try to come up with new features. Okay, you try to come up with new features. One approach is model-centric approach. Model-centric approach means you take all the features or the raw data as is and build a very complex model. This is one style of working. All the seasoned old data scientists do this, right? They bring in all the features, they build, they have enough data, build complicated models. Feature-centric mindset means you spend a lot of time coming up with new features. You use your domain knowledge. Okay, you build complicated features, but then you end up building a simple model. What model will you use in practical world, in real world? What model do you want to use? Obviously, a simple model, because you will use this model for a longer duration. Your training will be for a shorter duration. Using your model in production is called as inference phase or serving phase. You train for a longer duration and you use for a shorter duration, and then you use your model for longer duration, right? Usually. So I prefer being feature centric. I'm using the word I prefer this, but neither is this right nor is this right. It is horses for courses. When you use a horse for running race, use an appropriate horse. Some horse races happen at a higher altitude. You need different horses to win the race. Certain horse races happen in deserts. There you need different horses. So it depends. On similar lines, depending on the business problem, you either might want to become a model-centric data scientist or feature-centric data scientist. It's up to you. Right? So that's why I told I prefer being feature-centric. Okay. One of the classic examples that we keep giving is this. If you have these 4 inputs, raw data, time of previous transaction, place of previous transaction, time of previous transaction, and place of previous transaction, you're using credit card. Maybe you have done the current transaction at 10:30 a.m. and you have done it in Hyderabad. Another transaction you have done it on the same day at 10:45 a.m. of course, and you have done the transaction say in New Jersey, US, Hyderabad, India. Then if you use the raw data as is to predict whether a credit card transaction is fraud or not, then you'll have 4 inputs to deal with. So it'll be a function of 4 inputs. So your model has to learn patterns from all these 5. One is your output and 4 inputs. Using these 5, it has to learn the patterns, relationships. It will be slightly difficult. Using these 4 inputs, if you can come up with more derived variables, derived features, more derived features. Then so let's see what happens. So if you use time of current transaction and previous transaction, when you subtract both the time, you get the time lag. That is how much time was there between two transactions, 30 minutes. Within a span of 30 minutes, they've done a transaction in that. And then if you have place of previous transaction, if you have place of previous transaction and place of current transaction, then you'll come to know the distance. Hyderabad, India, New Jersey. What is the distance? Huge distance. How can someone do a transaction in 30 minutes or 15 minutes at such a, a distant locations? And if you have these two inputs now, then your output, which is whether a credit card transaction is fraud or not, depends on two inputs. It's a function of two inputs. You made your model simpler. At the same time, you're making this process slightly difficult, right? Using these four inputs, you're doing some calculations and coming up with new inputs. Can I do some more? Can I make it even complex? Yes. You use these two and come up with something called as velocity. What is velocity? Distance by time. Distance by time, distance divided by time will give you velocity. So you're bringing in some more complexity into building your features. But then you have a single input. If you want to classify whether your credit card transaction is fraudulent or not, you're having a single input now, which is better. Right? So you resort to whatever technique you want. Either you use your inputs as is. So simple. Take all these inputs, very simple. But when you build a model, you'll have to build a very complex model to have better accuracy. Or make your features complicated like this and build a simple model on that. Choice is yours. On what kind of mindset do you want to resort to? Do you want to be a model-centric data scientist or feature-centric data scientist, or somewhere in between? Is up to you. And please do not use your raw data as is. The data which is given to you by your customer is your first enemy. You need to attack it. How will you attack it? Say you have total credit card balance. You all use credit cards or debit cards. How much balance is there in your account? You should not use it as is. You always need to look at, it's not balance that I have in my card. What is my credit limit? First, look at that. Suppose I have $1 million that is given to me, okay, as credit limit. And then if my balance is $1,000, then you can say that, oh my God, this guy has used up a lot of money. But then if someone gives me $1,000 only as my credit limit, and if I have entire $1,000 as is, that means I did not use up any amount. If you use only the card balance as 1,000 USD, you might say that these two people have the same card balance, which is incorrect inference. Until unless you know what is the credit limit that you have, you'll not come to know what is the true picture. Here, this guy has used huge amount. This guy has not used anything. Maybe this person has a lot of debt. That's why he's using a lot of his credit limit. This guy doesn't have any debt, so he's not using. So maybe the needs of this person are less, the needs of this person are more. This is how you need to think about your features. Okay. Another thing is card payment. One person made a card payment of $1,000. Another person also made a card payment of $1,000. If you look at only this, you'll feel that these two people have done the same card payment. However, This person had maybe card balance of 10,000. Out of $10,000 that he has to pay, he paid only 1,000. Not a good customer. Out of 1,000, or maybe card balance, of course. He has a balance of this, and he made the entire payment. So maybe he's a good customer for you. This is how you need to normalize your features. Total debt. Customer A has $1,000. Customer B also has $1,000 as debt. Both of them have same debt. That's the kind of thoughts you'll get, right? But then if you look at what is your income, then it makes sense. This guy's income maybe is $1 million. 1 million is his income and only $1,000 is the debt. Good guy, rich person maybe. Maybe out of $10,000 annual income, this guy has 1,000 USD. Or maybe out of 1,000, he has 1,000. Do you want to lend loan to him? Not really. How will he repay? Because 1,000 is his income, 1,000 is his debt. Even better would be if you look at the distribution of debt or income, usually the distribution will be exponential. Meaning a lot of people on the planet will belong to either low income group or middle income group. Only a small fraction of people will belong to high income group. Exponential. COVID-19 cases also were exponentially rising. So when you have exponential data, to capture the patterns in the data better, you have to do log transformation. Okay. So why am I talking about all these things? Because a lot of people assume that magically data will come to you. You just give it to your algorithm, build a model, job done. And a lot of people put a lot of focus on models. Let me try this model, that model. Let me try a lot of hyperparameters. Let me see which setting is giving me the best accuracy. Sure, you need to do that. But even before that, the data that you're supplying to your model should be of good quality. Garbage in, garbage out, friends. Okay. Garbage in, garbage out. If you don't work on your data properly before you give it to the models, you will get junk model. Maybe 90% accurate, but in real world, it doesn't work. This is true when you face interviews also. If you are not putting in hard work in practicing your Python programming, in understanding the concepts or learning multiple times, then into your brain, garbage is getting in. Into your brain, you'll only get garbage. And when interviewers ask you, you'll spill out only garbage. Who will hire a person who has garbage in him, in his or her mind, right? So ensure that you internalize the concepts very well, like what we are doing here. We are not using this as is. We are using this as a feature. When you're learning, these are very important. Hardworking, perseverance, discipline. Okay, job will be yours with very high salaries. Okay, it's not just input variables, x1, x2, x3, not just those. You also need to look at, do you need to normalize your output variable? Say you want to predict the total sales. Is that a right prediction? Is that a right variable to be predicted? Tell me what will be my total sales. Can you predict it? Sure, wonderful. But then I need to look at what is your expected sales? How much are you expecting your sales to be? And what is the total sales? And then take a log of that. This becomes a very important output to be predicted, not just the total sales. Okay. If someone says, do digital marketing for me, okay, and when I use a keyword, some query, some keyword, Your company, my company URL should be in the third position at least. In the Google search, you'll have, right? When you search as data science training in Hyderabad, for example, you'll get 1, 2, 3, 4, multiple company URLs. Maybe this company is coming to you saying, please do digital marketing. When I search data science training in Hyderabad, my URL, my company details should be in the third position at least. Right? That's not a right thing to predict. You're doing something and you're predicting how will the rank improve. Right? Usually, what is the click-through rate you're expecting? CTR is click-through rate. I mean, when I show you an ad, will you click on that or not? Click-through rate. Or when my company URL appears here, are you clicking that or not? What is the expected click-through rate based on the position? If I put it in the first position, how many people will click? Second position, how many people will click? Third position, how many people will click? Based on that, you can predict your click-through rate. So this is a right way of normalizing your output variables. Okay. What's the time? It's, I think, time to take a break. I'll pause, resume. All right, let us get to the next step of understanding the types of models that we have. We have something called as inductive model. Inductive model is also called as semi-supervised learning model. Okay, that is what is inductive model, semi-supervised learning. We already discussed about semi-supervised learning. But the key thing here in inductive learning is that you train the model on the training data and you test it on the test data. However, your test data will be very different from training data. So if you have a data set, okay, you have, say, your output variable and your input variables, and say you have 10,000 observations. Okay. Say you train the model on 8,000 observations. Okay, so when you train on 8,000 observations, test data, which is next 2,000 observations, was never seen. Your model has never seen the test data. So you're training on the model and testing on completely new data. Whereas on the other side, you have something called as transductive learning, where if you have 1,000 observations, if you have a data set, output and input variables, output and you have input variables, and if you have all these observations, you train your model on the entire data set and you test your model on probably 2,000 observations from this. But when you're testing on this data, which is, say, from 8,001 until 10,000, you're taking these observations and then you're testing your model on this. When you do that, you know for a fact that your model has already seen this data also, because you are building your model on entire 10,000 observations. Remember, on the entire data, you're training your model. And once you get your model, which was built on entire 10,000 observations, you're testing it on 2,000 observations, which are part of your training data set only. So transductive model is that model where you train on certain data and you test on data which is already seen by your training model. Okay, the data on which you are testing has already been used for training. But in inductive, training and test data sets are completely different. You train on training data, test on data set which was never seen by your model that you train. That's the difference between inductive and transductive learning. Then you have online learning versus offline learning. Offline means batch processing. Maybe you will say that, do you know what? Let all the customers apply for the loan. Customer A, customer B, customer C, let them apply for loans. And at the end of the day, at maybe 7 p.m., I will take all these loan applications and I'll process these loan applications at 7 p.m. using my machine learning algorithm. So as in how one person applies, you're not doing it. Maybe person A applies at 9 a.m., B applies at 10 a.m., C applies at 1 p.m. for the loan. All these three at 7 p.m. you're processing in a batch. You're taking the batch of all these three and then processing using your machine learning algorithm. Online means as in how someone applies, you immediately apply a machine learning algorithm. At 9 a.m., someone applies for the loan. You immediately at 9 a.m. process the application, whether that person will default or not. At 10 a.m. when someone applies, immediately you process. If you immediately process, it's called as online or real time. Okay, online or real time. Offline or batch processing. For online or real time processing, you need very high compute, meaning you need high RAM, good processors, etc. For batch processing, you don't need high compute. Even with less compute, you can do the trick. With less RAM, with less processing power also, you can do the trick. So batch processing usually will cost you less. It's going to cost you less. Real time will cost you more, not less. Then you have generative versus discriminative model. Generative model means you just come up with a classifier like this. And say that anything which falls here will be classified as A. Anything which falls here will be classified as B. Anything which falls here will be classified as C. But suppose there is a new point which falls here. Okay, there is a new point which falls here. What will it be classified as in discriminative model? If you use discriminative model, what will it be classified as? A or B or C? What do you guys think? It'll be classified as A, because if you look at the classifier, the lines here and here, this falls in this area, so it will be classified as A. Using discriminative model, if you do, that is what happens. And a few of the examples of discriminative models, or I'll give you one example, is naive Bayes, probability based. On the other side, you have models. Sorry, my bad. This is an example. Naive Bayes is an example of generative models. Right? Sorry, my bad. So discriminative models are logistic regression, decision tree, random forest, logistic regression. All these are examples of discriminative model. This is how they work. And then if this is discriminative model, what is generative model? What generative model does is, it will learn the patterns like this. Like this. Like this. Okay. And see, let me properly. This is how it is formed. Now, if there is a new observation here, it will go to that class to which it is closest to. This is closest to C, so it will be classified as C, not A. And knife base is an example of this. So in short, depending on whether you use generative model or discriminative model, your results might vary. So it is always good to try out both and then see which one is giving you good result. Then you have parametric. In parametric models, you have parameters that your model learns. Like in linear regression, you'll have these beta values, coefficient values, right? These are parameters that your model learns. Okay. And you have non-parametric models like topic modeling, LDA, latent directly allocation, so on and so forth. These are non-parametric models. Okay, all right. Now comes the big picture, which we need to understand. And yes, certainly here is where sorry, I didn't enable my work. Where is a battery? I don't know. Okay, I think my
From my mobile, I've gone away. Sorry, Bluetooth is gone. So I've kept it for charge. All right, let's proceed further and understand more. So here, I need to probably okay, I'll explain the same slide. That's it. Whenever you have data set, you can either divide your data into training data and test data. You divide your data set into training and test, or you divide your data into training data set, validation data set, and test data set. Either you divide your data into training and test, or training, validation, and test. That's how you divide. You divide your data into only training and test when you have your machine learning algorithms which have no hyperparameters, for example, your naive Bayes algorithm has no hyperparameters. The best that you can think about is Laplace. There's something called as Laplace parameter. Or when you have less hyperparameters. Hyperparameters are the options within your machine learning algorithm which can be changed to experiment. Okay, hyperparameters are options within your algorithm which you can change to experiment. For example, in the algorithm called as KNN, this K value is a hyperparameter. And when it comes to decision tree, you have huge number of hyperparameters, like number of trees or number of estimators. Number of estimators. Number of trials. Okay, then you have the number of leaf nodes, the depth size. so on and so forth. Many things are there. Hyper parameters or options which you keep changing to experiment. Yeah, maximum depth is another hyperparameter. Right, so you have a lot of hyperparameters in that. If you have no hyperparameters or less hyperparameters, you just split your data into training and test. You need not experiment many things. However, if you have your data set where you have a lot of hyperparameters like deep learning, neural network. In neural network, you have huge number of hyperparameters. For example, there is something called as epochs, iterations, activation functions, batch size, optimization or optimizer. In that way, there are huge number of hyperparameters. When you have huge number of hyperparameters, also decision tree, extreme gradient boosting, random forest, these have huge number of hyperparameters to be experimented with. When you have huge number of hyperparameters to be experimented with, it is always good to split your data into training, validation, and test. Please remember this. Okay. Now what I'll do is, I'll first split the data into training and test, explain a few things, then I'll bring in validation, and then we'll explain further. Then we'll see how to evaluate the model. And during model evaluation, I'll talk about what if your output variable is continuous, what if it is discrete, what do you mean by entropy, what do you mean by categorical cross entropy, then what do you mean by binary cross entropy, so on and so forth. Sorry, I'm just trying to figure out a few things. Yeah, entropy or Gini index, but we will look into entropy, right? And then once we understand these aspects, we'll get into a deep learning primer. And then once the deep learning primer is done, all the algorithms is just walk in the park. You just need to understand a few key differences. Jump down. Trust me, if you understand this, all your machine learning algorithms, you would have understood at a high level. Then you look into each algorithm, what are the different hyperparameters? How does each algorithm work? That is all you need to focus upon. At a high level, if you know this, job done. Okay. So let me open a new slide. Let me go with black screen. Just that you would have, I'm sensing you are bored by looking at the white screen. So let's look at the black screen. Okay. So if you have your historical data, okay, so assume that you have an output variable and you have input variables. So you want to predict whether an employee will resign or not. A treat, not a treat. Age, gender, income, etc. And you have, say, 10,000 observations. Once you have a data set like this, you will have to split the data into training and test. If your data set is balanced, okay, if your data set is balanced, you randomly split. If your data is imbalanced, there are different other sampling techniques. Now assume that data is balanced and you're doing a random split and you're splitting the data into training and test. And say you went with a strategy that you want 80% of data into training and 20% of data into test. If you have more data in training, your model will learn more patterns. And if you have more data in test, you can be confident that you have tested on more data and you can be confident on the accuracy. If you randomly split, So you have your output variable and you have your input variables. Output and inputs. And randomly, since you have split, say row number 2, row number 3, row number 5, 7, so on and so forth. When you count 1, 2, 3 in that way, you'll have say 8,000 observations because 80%. Okay, you have 80% of observations. And the remaining data will be part of your test data. Save your output and your inputs. Output variable and input variables. The data which is not part of your training will be part of your test data. So row number 1, row number 4, because 1 is missing, 4 is missing, 6, so on and so forth. When you count 1, 2, 3, etc., you'll have say 2,000 observations because 20% of 10,000 is 2,000. 80% of 10,000 is 8,000. And then you build your model. Building the model means learning the patterns. Okay, so your model will learn the patterns between your output variable and your input variables. Say age is 23, gender is male, income is $10,000. So person has not untreated, means did not resign. It learned that pattern. So if the person's age is 23, gender is male, if the income is $10,000, then person will not retreat. It learned that pattern. So more the data, more patterns your model will learn. And these patterns are captured using some math equation. Using some mathematical equation, patterns are captured. Every algorithm has its own way of capturing the patterns, its own way of coming up with math equations. Then, if you're using, say, neural network algorithm, it will come up with an equation like this. Y is equal to B plus W1x1 plus W2x2 plus W3x3. And then, once you have your model in place, you test it on your test data. You are going to test it on the test data. Now, when you test it on the test data, is the test data part of your training data? Is row number 1, 4, 6, etc. part of your training data? No. If it is not part of your training data, if you're training on different data set and if you're testing it on a different data set, it's called as what model? Inductive or transductive? Inductive. Okay. So now that you have built a model, building a model is nothing but coming up with this equation. Now what are you doing? You're testing it on the test data. So you go to your first observation, you take your inputs, age, gender, income, substitute in this equation. When you solve it, you get your predicted value, which is usually given using Y and a hat on the top. So predicted value of this first observation, say it says that person will retreat or resign. Then you go and look at the actual value here. Say the actual value says person will retreat. Then you also know this, that the actual value is person will retreat. Is this a correct prediction? Yes. Actually, it is retreat. Predicted as this. Correct prediction. Okay. Then you go to the next observation. Take your inputs, pass it to your model. It will predict. Say it predicted that person will not retreat. But when you looked at the actual data here, it says person will retreat. Is that a right prediction? No, it's incorrect prediction. So a few predictions will be correct, a few other predictions will be incorrect. Overall, on all these 2,000 observations, when your model is tested, A few will be correct, a few will be incorrect. But to calculate accuracy, how will you calculate? Number of times your model has correctly classified divided by total. In total, you have 2000. So say your model has correctly classified on 1600 observations out of total 2000. So when you solve it, you get 80%. So your test accuracy is 80%. All right, test accuracy is 80%. Now, if you're happy with this 80%, wonderful. But if you're not happy with this 80%, what should I do? But even before that, we'll take one step back. The model that you built, you also test it on the training data. Hey, you built your model on the training data. Why do I need to again test it? Because you're coming up with one single equation for all the 8,000 observations. Can you actually fit in one equation for all these 8,000 observations? Will it work that best? We don't know. Let's see. For example, say you have output and input variable 6, 3, 4, 2, 9, 1. If you want to come up with one equation to capture the patterns of all these three, maybe your model will say y is equal to 2 times of x. Now, if you test this on this data set, let's see what happens. For the first observation, predicted value and actual value. Let's come up with predicted value. Take this input, substitute here, 3 into 2, 6. Actually, also it is 6, right? Prediction. Now, for second observation, take this input, substitute in this equation. 2 into 2 is 4. The second observation. 4. Actual value is also 4, right? Prediction. Take the third observation. Substitute 1 here, input is 1, substitute. 2 into 1 is 2. Actual value is 9. Oh, it's not giving right prediction. So, this equation that your model built was a generalized equation for your entire training data set. It's a generic equation for the entire data set. So when you test it, when you test your model on the same training data, it need not always give you 100% accuracy. So that is the reason why you test your model on the training data also, and then you get some training accuracy. Say you got a training accuracy of 82%, and here test accuracy was 80%. In this scenario, you say that your model is a right fit model. Why is it called as right fit? Because both the accuracies are more or less close to each other and they're high. What is the definition of high depends on your project. A few customers might say, hey, I want 90% accuracy. A few customers might say, I want 80%. Right? Or given your data, this is the best that you can do. You cannot increase it by more than 80%. You tried out all the experiments, but this is the best you can do. Right? Okay. Sometimes it might so happen that your training accuracy might be high, maybe 90%, and your test accuracy might be 80%. Then this is called as overfitting. Overfitting or variance. I think today we'll have time only to discuss this. Tomorrow we'll get into the loss functions, error functions, cost functions, and then the deep learning primer. And once we are done with deep learning primer, multi-layered perceptron or your CNN, RNN, we walk in the park. Okay, anyways, let's complete this. And in the due course, we have to discuss about a lot of regularization techniques, friends. Many regularization techniques exist. We'll discuss all that. Okay, let's talk about here. If your model is overfitting or if you have variance, you need to apply regularization techniques. In neural network, you have batch norm, dropout, drop connect, data augmentation, many things. We'll talk about this. And every algorithm will have different set of regularization techniques. We'll talk about it. If your training accuracy is less, then your test accuracy also will be less. And this scenario is called as underfitting. Or bias. If your model is underfitting or bias, then you need to get more data. Instead of 10,000 observations, well, probably you need 20,000 observations. Instead of 3 inputs, maybe you need 5 inputs. Okay? And then if you get more data and train, usually this issue is fixed. This is not a big issue. Overfitting is a very big issue. Solving overfitting issues is going to be a challenge. Now, this is like you preparing for the exam. If your training accuracy will be very high when you get a bunch of sample papers, sample exam questions. You prepare on that, and if you test it on this, if you test yourself on the same sample question papers on which you prepared, obviously score will be high. Usually it will be high. It will be very high if you by heart the question and answers. Because you by hearted the question and answers, when you went to the main exam, suddenly question changed. In the sample question paper, it was Ram and Shyam. Ram had 20 rupees, Shyam had 30 rupees, total how much did they have? But in the test, it was written as Sita and Geeta. Sita had 20, Geeta had 10, total how much do they have? Then you'll be confused because you by hearted. The moment I see Ram and Shyam, answer is A. To that extent, if you by heart, in the test, obviously, slight change in the numbers, you'll go wrong. That's the problem with overfitting. Underfitting means you brought a bunch of sample questions, but you did not even prepare well on those sample questions. So if you test yourself on the same sample question, you'll go wrong. Obviously, that's underfitting or bias. We need right fit scenarios. Okay. Okay, now I'll erase this and we'll get into a different mode of discussion. Suppose your customer says that, hey, I'm not happy with 80% accuracy. I expected more. Then what will you do with this information? You have no information because you tested on the test data. You have information that you got 80% accuracy. With this information, you go back and you change your hyperparameters. Change your hyperparameters. Hyperparameters are those options which can be changed. That is, this is also called as hyperparameter tuning. Hyperparameters. If you tune your hyperparameters or if you tweak, and then if you experiment, and then if you build a model, and then say you tested once again on your test data, this time you got a test accuracy of 88%. Then this is using model 1. This is using model 2. Model 1 and model 2, the hyperparameters change. Say you're still not happy. Again, with this information which you got by testing on the test data, you go back, change your hyperparameters, again build your model and test it on the test data. This time, when you build your model 3, these are all same models, same neural network models, but hyperparameters change. Here, say you got a test accuracy of 91%. Now you're happy. Customer told you anything above 90% is okay. So now you're happy. But then, can I compare this 80%, 88%, and 90%? When can I compare? Say student A got 80%. Student B got 88%. Student C got 91%. When can you compare these three students' marks? When they are prepared on the same syllabus. If student A prepared on state syllabus, student B prepared on central syllabus, and student C prepared on Cambridge syllabus or international syllabus, then you cannot compare these three. In India, we have SSC, CBSE, ICSE. You cannot compare these three results, right? When can you compare? When all three prepare on the same syllabus, all three prepared on state syllabus, for example. Then you can compare and say C has done good job. C has got highest marks. On similar lines, you can compare these models when these three models are built on the same data set. Usually what happens is, when you have the lines of code, in the first line you load the data, then you perform exploratory data analysis and data pre-processing. Okay, then you split your data into training and test. Then you build your model with, of course, hyperparameter tuning, and then you evaluate your model. This is how the code will be, right? Now, you built model 1, you were not happy with your accuracy. What do? You go back and change your hyperparameters here. And you need to run only from this line onwards. These two lines you need to run, or these two blocks of code. However, you will have an option to run the entire file. All the lines you can run. If you run all the lines, what will happen here is you're randomly splitting. So when you split here, again you'll have different data in training and you'll have different data in test. Right? Because you're randomly splitting again. If you're changing your hyperparameters, only running these two lines, fine. But if you run the entire file, again the data set will get split into training and test. You'll have different training data and different test data for your model. You got 88%. Again, you went back. Again, you change your hyperparameters here. And if you run these two lines, fine, wonderful. But if you run the entire file, again loading EDA split, again randomly it will split. Again, it will have different data on which you train. So model 3 would have been trained on different data set, model 2 on different, model 1 on different. To avoid such mistakes, accidentally you might run the entire file. To avoid such mistakes, all you need to do is, before you split, add one line which is called as setting the seed, random seed. Okay, this setting the seed, I'll explain here. If you say seed, you give any number you want, say you gave 20. This 20 will contain information that row 2, 3, 5, 7, so on and so forth should be part of training data. Row 1, 4, 6, so on and so forth should be part of test data. This 20 will have that information. So even if you run the entire file, It sees that, okay, they see 20, so 2, 3, 5, 7, etc. should be part of training, 1, 4, 6, etc. should be part of test. And when it splits, it will ensure that exactly these observations are part of training, exactly these observations are part of test. This way, what happens is, yeah, setting the random state. This way, what happens is, even if you accidentally run the entire file, you would have built all these three models on the same data. Why should you build on the same data? To compare the results, compare apples to apples. Okay, so this part is also, I'm assuming, clear. But there is again a glitch here. What is that glitch? That glitch is that each time you're testing a model on the test data, one section of people started calling this as information leak. What did they call this as? Information leak. This is like you go and take your exam. First time when you take your exam, you got 80%. We'll say that, okay, now that you got less, you go back, study well, and come back. When you're going back to study, you know that you got less. So you prepare well, and then again come and take the exam. You got 88%. Again, we give you another chance saying that go again, prepare again, come back for the exam again. And you'll be tested on the same paper, same data set. Again, you come and test 91%. So people call this as information leak. In some sense, some information you're learning based on the test, and then you're going back and tweaking your hyperparameters, again coming back. This is incorrect, is what people say. Test should be on new data set. You cannot say that I'll keep testing, I'll keep going back, changing hyperparameters, I'll keep doing it. You cannot say that. Is what one section of people believe in. And they came up with another split. And they told that in your training data, instead of 80%, have 60%. That remaining 20%, call it as validation data. Okay, call it as validation. And when you build your model, test it on validation data, not on test data. When you test on validation data, look at validation accuracy. If validation accuracy is 80%, if you're not happy, go back, tweak your hyperparameters, again test it on the validation data. This time, maybe you get a validation accuracy of 88%. Say you're still not happy, again go back, tweak your hyperparameters, again test it. When you again test it, this time maybe you got an accuracy of 91%. Now, are you happy? Yes. Once you're happy, take that model which you built with the hyperparameters of model 3, take that model and use that and test it on the test data only once. Once you test on the test data, if you get a test accuracy of say 88% or 90%, this would be considered as final. You built your model, you tested on validation data, you did all the experiments here. Never you expose your test data. The test data was kept as a very sacred data set. You never tested it. You are testing it now. After you figured out what is the best model, then you're testing on the test data and you got this. This accuracy, you need to communicate to the customer and say, this is the best. Okay. Now, if your output variable is categorical into categories. Categorical, and if you have two categories, two classes, then you resort to an accuracy measure by resorting to something called as confusion matrix. Confusion matrix is also called as cross table. Okay, or it is also called as contingency table. If your output variable is categorical, and if you have more than two classes, which is called as a multi-class classification problem, still you use the same measures, confusion matrix or cross table or contingency to calculate accuracy. And if you want to know error, then it is simple. If I get an accuracy of 80%, error will be 20%. What does that mean? That means that accuracy percentage plus error percentage should be equivalent to 100%, or accuracy value plus error value should be equivalent to 1. So if you can calculate accuracy, you can anyways calculate error. So these two are correlated. If your output variable is continuous, then directly accuracy is not possible. Then you need to calculate your error. How will you calculate error? You have various things: mean error, mean squared error, mean absolute error, mean squared error, mean percentage error, mean absolute percentage error, so on and so forth. But this is an important measure, mean percentage error. Say you got an error percentage of 10%. Then what will be the accuracy? 90%. So if you know error, you can calculate accuracy, or if you know accuracy, you can calculate error. When output variable is continuous, you can also use correlation coefficient. Of course, there are various other measures, friends. I'm sticking to most widely used. If your output variable is continuous, you usually calculate what? Error. If your output value variable is categorical, two class or multi-class, you usually calculate accuracy. Okay. Now, in the next class, when we connect, we are going to talk about information gain, entropy, cross entropy. In this, we look at binary cross entropy and categorical cross entropy. Why are we going to talk about these? Because my area of interest for explaining you all deep learning or neural network models is these two. Okay, and then I'll explain the difference between error function, loss function, and cost function. And a lot of things about regularization techniques, optimizers, and then I'll get into the neural networks. First, neural network algorithm, okay, and slowly we'll build on top of that. All right. So that is all I had for this module. In the module that we're going to connect next, we will talk about all these things that I've spoken about, right? And many more. We'll also resort to Keras, TensorFlow Keras way of running the code, and we'll also run the PyTorch code so that you have experience on both. And that will happen in the next module. We'll also do hands-on. Once all that is done, then slowly we'll enter into the convolution neural networks and recurrent neural networks. So thank you all so much for being patient with me, and thank you for attending the session. See you all. in the next section.